thanks to the organizer to giving me the opportunity of presenting my old work done with Liam and Ami in the audience and some work in progress together with Yuan. So this is more or less the plan for today's talk. So let's start from some introduction and motivation. So I believe that all of you know that the fuzzy sphere has become a very useful tool to access the spectrum of three-dimensional conformal field theories. In particular, in today's talk, we will focus on the 3D Ising CFTs, 3D Ising CFT. And this is just a plot of how the spectrum looks like with just n equals 10 electron as a function of the dimension and the spin. As you can already see that when the energy is high enough, the spectrum is really dense. So we have lots of operators with more or less the same energies. So it becomes incredibly challenging to try to define what's a primary and what's a descendant just based on integer spacing. So our idea is that then how we can try to select what a CFT primary is. And to do that, we try to construct conformal generators directly on the fuzzy sphere. And in particular, we would like to define a special conformal transformation generator, K-mu, such that we will call primaries all the states which are annihilated by this K-mu. And then we can build the entire multiplet just by acting with the translation operator. And this is going to be the first part of my talk. And then I will try to say something about what we can do with the CFT data that now we have access to. And in particular, I will discuss deformation of the original Ising CFT by some relevant operators. And in particular, by a sigma deformation, which break the Z2 symmetry, either by using directly the CFT data that we have access to through some Hamiltonian traccation technique, or also by trying to write down this Hamiltonian directly on the fuzzy sphere and analyze the problem there. So let me start from what we define and how we define these conformal generators. In a true CFT, we know that the Nader currents associated to conformal symmetries can be written in terms of the stress tensor. So this is the current written as a function of T mu nu, and the corresponding conserved charges are just the integral of the time component of these currents. And we will cite the theory in R times S2, and I will use embedding space coordinates for this S2. So I have this capital A index from 1 to 3, or sometimes I will call them Z plus or minus. And these are just coordinates when you embed S2 on R3. So the generators that we of the conformal group are like the dilatation, which is just the integral of T00. Then we have the generator of the SO3 rotation, which is just an integral times x of T0a, so also including the spatial component. And then we have a translation, a special conformal transformation. Let me emphasize that the sum of these P and K just depend on T00, and this is going to be relevant in a second. But this is what happens if you have access to the true stress tensor of your CFT. But the fuzzy sphere realizes conformal symmetry just in the IR, so it's like an emergent symmetry. So any operator we can write down on the fuzzy sphere is not going to be just like one local operator in the CFT in general, but we can still write it down as an infinite sum of local operator in your CFT. So the idea is then how we can access this T mu nu. So maybe the easiest possible thing to do is to construct T00 directly from the Hamiltonian density. In fact, we know that when integrate the Hamiltonian density, this gives you the Hamiltonian, which is the generator of translation. So that's like a good motivation why H should be your T00. And here I'm just writing down the Hamiltonian density in the fuzzy sphere, where we take the original prescription in which we are including just the n equals 0 and n equal 1 coupling, so just like a quartic potential with no derivatives or with 2 derivatives. And then we have the transverse part. this is, so I can just like try to write down T00 as a function of, as a combination of H plus plus some perturbation, in the sense that the operator in the fuzzy sphere can be written as the CFT stress tensor times in principle an infinite sum of local operator. At the level of the Hamiltonian density, I can write down every operator with preserve my symmetries. So they should be SO3 scalars, they should be Z2 even, and also parity even. And in this sum, I should include both primaries and descendant operators. But now the magic in H is that since I'm integrating this over the sphere, the only operator that survive here are just like primary operator. So my H is just the H of the CFT times this gamma factor, which is the speed of light, plus a sum with some coefficient that we'll call Wilson coefficient of primary operators. And it is important to notice that these Wilson coefficients, they are not per se are not dimensionless, so they scale with my lambda uv over IR times 3 to the minus delta O being the dimension of this operator. So in particular, as a function of n, the number of electrons, that's the scaling that we expect. And our primary goal will be to try to tune away, first of all, like the first relevant deformation, because you see that with delta O it's less than 3, this grows with n, so we want to get rid of this operator, but also we would like to get rid of this epsilon prime, which has a dimension which is like pretty close to 3. So this is the general setup. Are any question about that? It's important that we can write down these as like a sum of local operators. So how we can try to tune away this epsilon and epsilon prime deformation? The idea is to use conformal perturbation theory and try to tune the parameter that I showed you before in the Hamiltonian in such a way that we can remove these two contributions. So remember that that's the definition of H. So from here I can get that the corresponding eigenvalues can be written as the true conformal dimension times the correction coming from having this additional operator. And these are the expression for this correction, which notice they can just be written in terms of OPE coefficient of the operator you are perturbed by, and some other dimension depending if the operator you are considering is either a primary or a descendant. And in our approach, we want to use the known bootstrap data for low dimension operator in such a way that we can actually construct these quantities. And then in order to tune this lambda 0, lambda 1, and H, we are trying to minimize the difference between what we compute on the fuzzy sphere and the expectation at linear order in this G coupling. So that's the quantity we're going to minimize, and here is how we do that. So we fix the number of electrons to be 12, and here I'm plotting this G epsilon, which are the dashed line, and G epsilon prime, which has the solid line as a function of V0 and for different values of the H parameter. Now the operator in which I'm minimizing over are this subset, but we check that it does not matter much of like how many of these operators and which operators you are including, even if it's important that you include at least these 3. And we want to define our fixed point in the as the point in which both these G epsilon and G epsilon prime they are 0, and we find that the point is H equal to this value and V0 equal to this value, which is really close to the original fuzzy sphere fixed point. And just as a reminder, this V0 and the V1 related to the lambda 0 and lambda 1 that I showed you in the Hamiltonian. So this is the fixed point we are going to use all throughout the talk. And that was what concerned the dilatation operator. But now let's move on to the maybe new and more interesting generators, which are the translation and the special conformal transformation. As anticipated before, we are going to construct not P and K separately, but like the sum of the two, because these just depend on T00, and that's the thing that we have shown that you can just write down as a function of the Hamiltonian density. this is partially also because if you were to try to write it down, these starting from the T0A, it's kind of and use the same T0A that you are generating the SO3 rotations with, it becomes like basically this result is going to give you 0. So it's convenient and also necessary to compute just the sum of PA and KA. But this does not mean that we don't have access to both PA and KA separately, because we can use the conformal algebra to actually construct the difference of the two. You just have to take the commutator of the dilatation with this sum, and then you can disentangle PA and KA. This is what you should do, but what we do in practice is that we define P as P and K as the matrix element of this lambda, such that they increase or decrease the energy. So let me, to explain this, let's look at this picture. So these are the matrix element of lambda z, so the z component. Recall that A is the ion embedding space coordinate, so we have z plus and minus. And these are the the expectation, the absolute value of the expectation values of lambda z in between like different operators. This is plotted at n equals 16, and this is the difference in the energy level of this I and this j term. And you see that without doing, just like implementing this directly on the fuzzy sphere, you see that we have two spikes, one around 1 and one around -1. So we define P as all the matrix element in which this delta ij is greater than 0, and K all the matrix element which is where delta ij is less than 0. And here you see that it's like quite incredible that you already see that these P and K are merely like increasing your energies, or better, your dimension by 1.
Can you explain a bit better why you making this description?
Yeah, first of all, we checked that doing this is basically equivalent to taking this prescription. It just
Which I don't know, I missed. What is the better prescription?
This is just easier because what you compute is like lambda z between I and j. So that's what like you compute this from the fuzzy sphere. So you have access directly to this rather than compute like another commutator with this quantity. It gets like longer because you have to do like more steps.
Just numerically it's more expensive, or
yeah,
it doesn't.
It's no, it's numerically just expensive. We checked that is actually the same.
But
more or less,
d here would be the integral of h that you already constructed.
Yeah. So this may be that there's also like some propagation of errors when you try to do this rather than.
But have you like tried to compute P and K separately?
Yeah, we have tried like if I recall correctly, we have tried like a lower truncation, and the results were like not so much different. Also because then we are not gonna just like take this value. We're also gonna do something with this lambda a. So that's gonna be relevant in a second.
But I still don't understand. What does it mean? Take this and assign it to P.
Yeah, I'm just saying that here you have a matrix lambda z with I and j. And you define, so you have like this matrix element, and you can compute the difference in the energy between the element I and the element j. And if this difference is greater than 0, you say that this lambda z is equivalent to p, z.
But clearly this is not, you can make a prescription, but this p is not exactly what you expect from p, because it has, for example, some energies are increased by 0.5, which p shouldn't do.
Yeah, obviously it's not a perfect definition of p,
okay.
but it's still like good enough.
Okay.
I mean, you can define a little window around 1 and -1 if you want, but then it's that introduces some ambiguity in how you decide it. This choice, I thought it was slightly better in terms of when we checked the commutators.
Yeah,
and the idea is that sort of keeping everything, which is positive change in energy, when you compute the commutator, you're summing over intermediate states, and that was a little bit more accurate versus if you were to select a window, then you throw out some intermediate states. These were small differences, but it was slightly more accurate to do it this way.
Also because, another thing is that when you compute these things at n equals 16, you're not really diagonalizing the full matrix, so you're also putting a cutoff in the dimension that you're considering, and that's like slightly better than.
But can you, for example, assure us that the points that have wrong eigenvalue of P,
like this one?
for example, these ones, that these are some junk points corresponding to very high energies or something like that these are not states that you're supposed to.
Yeah, it gets worse.
Yeah.
You can't tell on this plot, but it gets worse as you look at higher and higher dimension energies. So as the lines, the noise around one gets bigger as you include states at higher and higher dimensions.
Yeah, I'm gonna like refer to this like later in like in a different slide, which maybe it's gonna be clearer what Liam means by saying that they are bad. But as I was anticipating, we still have to do something with this conformal generator defined in this way. Is basically before I was okay, we can start from H here, but the magic that was happening for the Hamiltonian, mainly that when you integrate, you just have primaries operator here. That's no longer true when you have all these additional XA. So when we compute these lambda tilde A, we are still polluted by the presence of descendant operator. So now the GO that I was the O with GO that I was summing over are not just primaries but also descendant, and is like a plot to convince you that that's actually the case. So this is the same matrix element lambda Z in between the vacuum and the first descendant of epsilon. In a true CFT, like really at the fixed point, you would expect this matrix element to be 0. But when you compute this as a function of 1 over n, you see that it actually seems that this increases, which might be saying that, oh, this definition is bad. But if you try now to fit this point with the expectation, so mainly that you are polluted by the presence of descendant of epsilon, for example, you see that the actual fit goes to the correct value, which is 0. But obtaining this value directly, like at some fixed n, will be impossible because that will require to go to n, which I don't think is like possible. So. The idea is that, then how we can remove these descendant states, and so this lambda tilde A, and we are saying that we are polluted by all possible descendant, so the descendant of my operator O. But then you can commute this lambda with this XA and see that you can just write it down as some sum over all these possible descendant times the integral of your primary operator. Now, it is true that all these G, they have a different scaling because they come with different derivatives, but still we can think of removing all of them together just by fixing some other tuning parameters. So more concretely, we can write down lambda tilde similar to what we have done for the Hamiltonian. So there is a rescaling factor coming from the fact that we can also remove descendant of T00. And then now we have a sum over primaries times this G effective, being G effective what I call this sum, which is in principle an infinite sum of descendant, times like the integral of the primary operator. And so what we can try to do is that use the same V0 and H we have used to tune the Hamiltonian, give them like a slight deformation, so the delta V0 and delta H, and try to remove also this additional contribution. In particular, we would like to remove descendant of epsilon, epsilon prime, and T00. And how we ensure that? We impose this matching condition. So we impose that the expectation values of lambda tilde Z between the vacuum and the first descendant of epsilon must be 0, as prescribed by the CFT. The one also with the second descendant of epsilon should be equal to 0. And then to fix this gamma effective, we impose like a rescaling in the sense that the lambda Z between epsilon and its first descendant should be fixed by the value that we expect from the CFT.
Can you explain what do you mean that you use V0 and H?
Yeah, basically when you compute this lambda tilde as a function of H, you just keep all the parameters that you have in the Hamiltonian, you give them like a V0 plus delta V0, for example. So you can use the same parameter and you don't have to recompute anything. You can just use the same matrix element that you have before. And
So you will still use the other values that you already tuned to compute the spectrum, but when you compute the generators, you use slightly different values.
Yeah. Basically, you still start from this, and you have like your intra-XA of your H, and this depends on the V0, V1, and H. So you have already an expression like this, and then you say, oh, V0 is delta plus V0, and you fix this delta, basically. Yeah.
And you're allowed to do this because of the point on the previous slide, which is that lambda gets contributions from descendants, but when you integrate by parts, those contributions are exactly the same as if there was a shift in V0 or in H.
Because they're coming from the same operator. Okay, so now we are imposing this matching condition, and that's like a visual proof that this actually works. So this is the epsilon multiplet, so this is the dimension, and this is the L. And I should say that now here we are really using like integer spacing, so these values are like really the eigenvalues that you get from diagonalizing H. And here I also say what's the expectation from the CFT versus what we get from this fuzzy sphere implementation. Okay, this is 0% just because that's what we fixed to be. The same value as the CFT, but you see that the red, which means that it's good, is like a lot more than the other colors. So that's just to showing to you that imposing this matching condition is actually doing like a very good job. And this is an example for a Z2 even operator, but we can also try to do the same for the Z2 odd, so the sigma multiplet. So here I'm showing like the same figure, and you see that the red is, we have a lot of red, which means that it's like really good. Okay, but now what we are gonna do with these new generators, we can try to construct primaries. So the thing is that if you just,
yeah, sure. I missed something. So you were explaining now how to, so you were trying to, how to construct lambda, right?
Yeah, we're trying to construct lambda, which is k plus p. And then...
And it was an integral of x t00.
xa t00.
Oh, t.
Because it's p plus, yeah, I think I have it. Yeah, this one.
Right. Okay. And then you said that h is like gamma t00 plus...
Yeah, then what we did something similar to tune as we have done for the Hamiltonian. So you say that T00, in the Hamiltonian we're saying that T00 is like some speed of light times, that H is like gamma times T00 plus contribution from primaries. But now you also have a contribution from descendant. That's what I was saying here.
But T00 is a Hamiltonian density on flat, right?
I mean, what do you mean? No, everything is like done in R times S2.
Okay,
yeah.
The original Hamiltonian, the spectrum was, H and V0 was chosen so that, the spectrum is as closest to Ising as it can be, right?
Yeah.
Can you explain again why are you now changing those to realize the specific P plus K that does the best job, but
yeah, that's part of like Liam's point is that since you are like deforming basically by the descendant of the same operators that you're tuned like to fix the spectrum, you're still allowed to like move a little bit this V0. It's not that you're moving them by a lot. That is.
But if you recompute the spectrum of the Hamiltonian.
But I'm not changing that V0 and V1. These are like new. Yeah, maybe that's like bad notation. There are some V0 prime and H prime. Yeah, I still keep the V0 and H to be for the Hamiltonian. I keep V0 and H to the value that I showed before. These for like fixing lambda tilde A are new V0 and H, but I will never recompute the spectrum.
They obtained from the same Hamiltonian.
Right? Giulia, why don't you show the slide where you showed that descendants? Yeah, where the descendants have. So the point is this slide here that in the Hamiltonian density there's an infinite sum, not just over primaries but over descendants. And in the last line on the slide, you see, consider any descendant inside the Hamiltonian density. You can integrate by parts, and it gives exactly the same contribution as the primary, but with a modified coefficient. And so the point is, the Hamiltonian density has a bunch of descendants that contribute to P and K. They don't contribute to the Hamiltonian because they're total derivatives in the Hamiltonian. But they do contribute here because you have that x hat inside the measure. So now our descendants do contribute. So now you get additional contributions to P and K, which have exactly the same form as the primaries. So they act like chain modifications of the coefficients. Does that answer your question?
What's confusing me is that the original Hamiltonian gave me all the descendants as well.
Yeah. Can I ask Kenny, because I think I understand it. I also had the same confusion. So the point is that they use the original Hamiltonian which they tuned to compute the spectrum. They no longer touch it. They always compute the spectrum with that Hamiltonian. But when they compute the generators, they use a Hamiltonian with slightly different values of V0.
We just tune the generators. We don't touch the spectrum or the eigenstates.
It's
And which seems to be okay to me. Yeah, that's nice.
I understand that. It's not clear to me that where the extra freedom came from. I mean, you're realizing some lambda.
Because when you like, okay, let's oversimplify and let's say that epsilon is controlled by h, for example. Like removing epsilon is the same as like controlling the parameter h. And when you define the Hamiltonian, basically you never see these because these just integrate out when you integrate just h. So all these descendants here, when you have like, since they are total derivative, when you compute h, they just integrate out.
I understand that. I just don't understand why this will then. Okay, maybe I understand it.
Yeah.
All right.
And also, it's because you see these descendants in P and K and they don't show up in the Hamiltonian that you get this 1 over n to the 0.2, and that's why the convergence is so bad here. The descendant operators don't contribute in the Hamiltonian because you can integrate their total derivatives, but they do contribute here, and that's what's screwing up the convergence, and that's also why you have to remove them, and that's why you also have these additional parameters to remove the descendants in.
Yeah, thank you.
Okay, so now what we do with this P and K is that, as I was saying, now we want to say that a state is called a primary if it is annihilated by Ka, and then we construct the multiplet by acting with PA. This is like just a representation of what just like an energy eigenstate look like for T prime, for the T prime multiplet, versus with our definition of what a primary is. Where this is just like where the new primaries, the K primaries are just a linear combination of the previous energy eigenstate. But let me show you maybe this multiplet, which I think is more expresses the point better. So it is the Z2 even spin 4 operator. This is what we will look like if we just use integer spacing, like to define what's the primary is and all its descendant, versus what we obtain by imposing that K should be almost 0. And you see that now the dimension changes because now this operator is a linear combination of the previous one, and you see that by defining the operators with K and acting with P, the matching with the CFT expectation is much better. Like it's particularly the error goes from 300 to like 20%. So that's like for us was a proof that that's like a better definition of what you define a primary and how to construct the multiplet. Now this is just like another test that we have conformality. So this is our K and our PZ, and we know that in a CFT the commutator should just give you H. So here I'm plotting this the commutator of KZ with PZ versus the dimension, which is the expectation values of H. And you see that that's also referring to Slava's first question. They see that some of these states, they are getting incredibly bad when the dimension gets like incredibly higher.
So but actually, sorry, I had a question about your previous slide. I'm sorry, I have too many questions.
Sure.
So, because you went a little bit fast. So you now want, so before you had the special class of states which were H eigenstates.
Yes.
Now you want to introduce another special class of states which are going to be K eigenstates.
Yeah.
And you want to say that this is somehow better.
Yeah.
But aren't you just, now you're going to be better on this side, but now there's going to be some problem on the left part of the plot. So aren't you just like shuffling the problem from one generator to the other? So in which sense is this better? Because you still don't, because the conformal algebra has all generators. You're just telling us that you're not able to implement all generators consistently. That there's always some problem, some small error somewhere. So why is the other error better than this error? So, is there some objective way to say which error is better?
I mean, one thing is that this procedure at least tells you that in the at the energy, like around some energy, in which you have lots of operators, at least you have some condition that tells you, oh, this might be a primary, which you didn't have before. So at least it's a condition which tells you, like, oh, this should be a primary.
We also measure the Casimir.
Yeah, also, yeah.
And the Casimir is better.
So yeah, the Casimir will be like saying that also the energy that gets better.
Yeah.
So and here the point is that you see that after some point it seems you will expect that the different you would expect that good operators, they just lie on this line, but you see that after some dimension most of these operators, they don't. So we take this as a very rough estimate of where our lambda UV cutoff is. This is really just you can say that, oh, this lambda UV cutoff is between, like, is where these states they get to be bad, so they are like away from this line. And here, just to show you that when you put this cutoff and you do it like throughout different values of n, this has the scaling that you would expect. So it's like square root of n.
Which is what you would expect. It's just the coefficient.
It's just the coefficient that we get.
10 is surprisingly large.
No. The reason why we say 10 is that we fix like this. Yeah, we fix it like at 10 just because it's the maximum value in which we can like access all the spectrum. Yeah, so we fix it like to be this. So it should be like around 5 actually. Yeah, that's what I was saying here. It should be around 5. Okay. So and now this is like a plot of what we will say that they are primaries. So this is for the Z2 even operator, and a good primary for us is a state in which k squared, where now is really k squared, not just kz, but you have kz squared plus the k plus k minus. So we would like to have k squared to be small, and also this commutator to be, the commutator divided by 2d to be close to 1. So all operators like in this region, we consider them to be good primaries. And here we have been really conservative, so we really like allow for a very small region. And we see that in this way we could recover most of the primaries that were we know from the bootstrap. And then, okay, I didn't put like lots of dimension here, but the dimension are really close to what one would expect. Perhaps also this can be like a good state, but to be conservative, because this is really close to this, but to be conservative, we just like kept the one which are really in this like tiny region. And this was for the Z2 even states, but we can do the same also for the Z2 odd states. And again, here we have like sigma and all the other states. Which was like, I think, a great result that we can recover already all of these operators, and we can safely remove descendants.
But if those other states are also primaries, the black dots, would it be some primaries which have not been discussed by the bootstrap?
So far, with this data, we cannot say that. In this very conservative setup, we cannot say that we will see other primaries. At least not at n equals 16. Maybe you can do this analysis for like a higher n. You can try to do like to maybe improve this measurement.
But can you say like why do you not include the point 6.65, 4? the first black dot.
Yeah, I mean, it was like, yeah, we,
Bootstrap hasn't seen it, or
no, because we put some cutoff of what we consider like to be good, and we said that this like is the region where we, I mean, if
But
we...
is it a coincidence that your cutoff sees precisely the same states that the bootstrap has seen?
I know, I
Or
don't
was it
think
how
so.
you chose the cutoff?
No, it's not how we chose the cutoff. We chose the cutoff like, I don't know, I mean, I cannot say that was not, I was not...
Did you do a blind analysis?
I mean, I knew so much. I cannot do, no, I cannot say so, and I'm not going to be completely honest. But if I were like that, why I didn't include that? That's like very close to this. I could have included this as well.
0.2 is also a small number, so.
I could have included also this. Yeah, I agree. We decide. I mean, this is like there is some choice here on what you can say like a good primary or not. I'm not saying that it's like God given say that God tells me that, oh, that's where you should put this cutoff. This I cannot say.
You should go to larger and larger system size and see whether.
Yeah, exactly. You can also do that. You can.
Have that.
This one, yeah, this one, yeah, is this one.
Okay.
And also, yeah, another thing is that I want to point out that if we believe our lambda UV cutoff, this is also telling you that you should not consider states which are too high in energy. So at 16, you will say that you can just reliably say that just this, that like for example, like something at dimension 7, you would not say that n equals 16 should be like considered like a good primary. So. Is a combination of these assumptions. Okay, so that closes like the first part of my talk about what we have been, the work that we're doing with these conformal generators, and let's move to the second part of the talk, in which I try to do what we can do with this CFT data. So let me start from like maybe a model which is more familiar, which is the 2D Ising field theory. So let's start from the transverse field Ising model in 1+1 dimension. So this is the spin Hamiltonian, and we know that the fixed point is just when this parameter is set to 1. Then we can add magnetic deformation. So we add some Hz times the sigma Iz. And it is known that when we turn on this parameter, the system enters a massive phase. And the bound state of this theory are known because the theory turns out to be integrable and have been computed. In terms of this coupling is dimensionful, so this M gap is just given by Hz to the 1D minus delta sigma, which is in this case is Hz to the 815. And this is how the energy gap looks like as a function of this Hz parameter for different values of the lattice size. And you see that all this line, maybe apart from the L equal to 3, they flattens out. And this is like what we will call, like what we would expect to be the mass gap. Because you see that this mass gap goes as this power, so if we divide the energy by this power, like the constant term is what we expect to be our first, the mass of our first bound state. And the reason why this line flattens out really quickly is that because finite volume effects in this 2D theory are exponentially suppressed. So you see that going from 3 to 12, this improves like a lot, and we already see like this line, which is basically flat all over the Hz parameter. And that was the story in 2D. So what about 3D? Can we expect like a mass gap? What we can say about the three-dimensional version of this problem? And this is just an invitation of what our preliminary results are so far. And now I'm going to explain more in detail what was going on. So in 3D, we do something similar. So we have our action, which is the action of the 3D Ising CFT plus deformation by sigma x. And this is the same plot that we have shown, that I showed you before, of the energy gap divided by Hz now to the power z.4, because we are in 3D as a function of Hz. And here I'm plotting two different results obtained with two different methods. So the points are the fuzzy sphere obtained at n equal 24, and I'm going to tell you in a second how I implement this on the fuzzy sphere. And the other one is the result from TCSA with delta max is equal to 6. And before discussing, I will describe in a second. It was just to say that first of all, that we don't see this flat line already. And the second one is that these two methods are really close to each other. But now let me say in details what we are doing and what TCSA is. So in the fuzzy sphere, I start from the original Hamiltonian density, and I'm just adding NZ. NZ defining this in this way in terms of the fermions on the fuzzy sphere, reminding that NZ, on the fuzzy sphere, we cannot just implement the sigma operator, but NZ contains sigma, descendant of sigma, and all possible operators, which are Z2 odd, and each of them has a different scaling. And we can actually try to compute how much of sigma you have inside NZ by studying, for example, the 2-point function of or expectation values of this kind, as it has been done in this paper. So this is what you will get when you try to implement this kind of deformation of the Hamiltonian at n equal 24. Let me spend a few words on how we should interpret, or at least how we interpret this plot. So when hz, hz is basically h tilde times this lambda sigma. So when hz is small, we expect the perturbation by this operator to be really a perturbation. So we expect that the energy gap is just quadratic in my coupling. And maybe it's not super clear from this plot because I'm dividing by this weird prefactor, but if you plot it just E gap as a function of hz, you see that the first part is really quadratic. And then we have this, I didn't plot it here, but when hz is really large, you can imagine that I'm basically diagonalizing just this term, so everything just becomes trivially linear in hz. But the region that we are really interested on is the one in between. And for this one in between, where ideally we would expect it like a very flat line, we don't see it yet. And the fact is that in this system now, the finite volume effects are no longer exponentially suppressed, but they are like power law suppressed. So that's why we don't see like this flattens out like quite already. So what we can try to do is that we can try to define a region in which we do believe that we see this type of effects, and that's where the original plot was helping us identifying this region, and try just to fit with what our expectations are. So just a reminder that M is related to decoupling in this way. So this term, the constant term, corresponds to the mass, and this other term corresponds to this power law suppression. And then we can try to do the same by in this different setup, which is called TCSA, truncated conformal space approach. So the idea is really similar. So you start from an Hamiltonian, which is made by the CFT Hamiltonian times the perturbation by a potential, which is just the integral of your sigma x. And then you can, in principle, you should diagonalize this Hamiltonian, which is infinite dimensional. But you can do that, you just decide to put a UV cutoff, namely that in this HCFT you don't include every CFT operator, but just a subset of states with a dimension which is less or greater than lambda UV. In the simple setup that we have worked so far, we're putting this cutoff really low. So we are just including all the scalar state with dimension which is less or equal than 6. So this means that in this HCFT part, we are just including this operator for the Z2 even state and this operator for the Z2 in the Z2 odd sector. And the Hamiltonian looks like this. So we have the CFT part, which is diagonal. and it's just given by the dimension of this operator. And then we have these two of diagonal terms, which mixes the Z2 even and the Z2 odd sector, and they're just given by the OPE coefficient between these operators and these operators. Now, at this very low truncation, all of the dimension and the OPE coefficient were already known, so we were like good to go, and just diagonalize this matrix as a function of this HZ.
How do you know sigma, sigma prime, epsilon prime?
I think that was taken from the fuzzy sphere paper. I think you computed that. Yeah, we're taking that. Yeah, this was also like why we will need like to have access to these new OPE data. So yeah, I have to say that this is really preliminary. So there might be like we should like account for the fact that maybe you have some error in computing also this OPE coefficient. We haven't done yet. We haven't done it yet. So, and that's what it looks like. So now the red solid line is what we obtain from this approach. So basically we're just diagonalizing this matrix as a function of HZ. That's what we are doing. And first of all, so this is my H on the fuzzy sphere versus the one in the TCSA. So first of all, I wanted to emphasize the fact that these two lines are really close in the IR, where we expect them to be really close because the IR effects are basically the same in like in this approach and in this approach, and especially when H is really small, everything is just quadratic. So we can also use that the fact that these two should be the same at small values of H to just rescale this parameter. So this perfectly lines up, and then you see that the region in which you can still say that they are kind of similar is the region why where we wanna fit against our expectation. So our expectation being like that the energy gap should behave in this way. And then they deviate because UV effects are like different in this approach and in the fuzzy sphere approach. And quite incredibly, when you fit both TCSA and the fuzzy sphere, we obtain that the mass is really similar, and also the coefficient of m squared divided by r squared, which you can see as the size of this bound state is also really close. So that's already impressive. And I should say that the fuzzy sphere we have to go to very high truncation, while for TCSA it's still like kind of like a very low truncation. So one of the things that makes really hard to go, like maybe to extend this region, is that the fact that the fuzzy sphere has lots of UV effects coming from different sources. One is that NZ is not exactly sigma, but it has pollution from descendant and other operators. And also, it is important to recall that the state that we get from the fuzzy sphere are not exactly CFT states, so they also get corrected. And so the idea is that we actually need to improve this result. We should really try to remove these irrelevant operators even better. So what we start trying to do is like to reanalyze what doing a new analysis of this Wilson coefficient. So
yes, sure. For the fuzzy sphere data, how do you fix the speed of light?
Here we fix like you can do two things. Here, when you have like this E gap, you can either like fit this part, the G square part, to be to like align with what you would expect from TCSA. So this gives you like a general rescaling, or you can really like study like this coefficient and just you use the fact that this times this and you plot as a function of this. But that's it's equivalent. Okay, so we were trying to remove these UV effects. So let me remind you once again that every fuzzy sphere operator is just like an infinite sum of local operator in the CFT. So this is what happens for the Hamiltonian density that we have seen before. And this means that also the states, the eigenstates, they get corrected. So the O tilde that I have on the fuzzy sphere is the CFT one, but I also have this correction, where in principle here I'm summing overall possible descendant. In general, every operator that I'm trying to measure is polluted by the fact that this is not just the operator that I'm expecting, but I also have other operators. So this is just an example for NX. So every time that I do some measurement, I have this the fact that the operator is not exactly what I will write down in the CFT, and the fact that the states are not perfectly the CFT states. The good thing is that this part just depends on the Wilson coefficient, the dimensions, and the OP coefficients. So for low energy state, these OP coefficients are known from the bootstrap. So having like a good understanding of what these Wilson coefficients are as a function of n is actually it will allow us to have like some control over these UV effects. So this is so once again the energy is gonna be the energy from the CFT dimension. Instead of having the speed velocity, the velocity of the speed of light, here we have the coefficient of the stress tensor plus the correction from the operators that we are perturbing by, which are proportional to the OP coefficient times some factors, which depends if this operator is a primary or not. And the primaries that we are going to consider now are not just the epsilon and epsilon prime we have been focusing on the first part of the talk, but we also allow some other higher dimensional operators, so also C and T prime. And the reason why we still believe that you still have to fix better is that even if we are at the fixed point now, when you analyze, we are assuming that R is just proportional to n in this plot, and just plot this as a function of 1 over n. And you see that ideally, if these were all 0, you would expect just this to be flat as a function of 1 over n, but that is not actually the case. So this is just like an additional motivation why maybe we have to do this tuning better.
But which tuning is done here?
No, here is, yeah, this is just that I take whatever the fixed point that I said at the beginning was. I'm just like replotting the dimension of sigma and the dimension of epsilon as a function of 1 over n. These I'm not doing anything. These I'm just like plotting what I get directly from the fuzzy sphere. There's no plotting involved here. It's just that I'm at the fixed point that at n equal 12, I believed it was the one in which g epsilon prime were 0, and I'm just now plotting as a function of 1 over n.
But you did tuning at some particular value of n, and now you vary n, so maybe the tuning that you did.
Yeah. I agree. Yeah. They were just like, yeah.
Many things which can happen.
Sorry?
Many things which can happen.
Yeah, exactly. So it's just like, yeah, there was just like a plot as a motivation. And the idea is that if I were just to try to fit all possible deformation here, just basically from like these 2 dimensions, the fitting is really unstable. So our idea is that maybe we can cook up some combination of observables such that it's easier to access some of these Wilson coefficient. So what we were trying to do is that, for example, to construct the idea is that we would like to isolate as many Wilson coefficients as possible. So, for example, we can try to construct differences of the dimension of a primary and like different descendant. And this way we can cook up like a function in which g epsilon is removed. Then we can, for example, construct like ratios of these differences. In this way, this dependence of g tilde is removed. Or also like constructing combination of different ratios in such a way that we can remove g epsilon. So in this way, for example, I can just isolate the contribution from C and T prime. And this is what we get when we try to compute like this kind of combined observable. And this is like a plot of this quantity versus 1 over n for different values of n. And here I'm just plotting the result that we get from the fit, in which in the fit I include either all the n that goes from 6 to 26, or if I include like less and less points. And you see that these plots are actually much more stable to what we would have get just by trying to fit these quantities alone. And this is for GC and GT prime, which are the most irrelevant operator that I'm including. But we can try to do the same also for G tilde and beta, where beta is just coming from the fact that my R is not just square root of n, but can also have a subleading correction. So in this particular example, beta is just G tilde times this coefficient that I call alpha. This is like a more complicated combination of the differences, and you see that also in this case, these numbers are quite stable, including more or less points. So let me conclude. So this is just like a summary of what we have seen today. So we have described how to construct conformal generators directly on the fuzzy sphere, and we have used these generators to define primary operators. And in the second part of the talk, I just present some new result of how we can try to use this CFT data or like directly a fuzzy sphere realization to start the study of the 3D Ising field theory. And this is our point for the future. So I've just shown you like 2 plots of this analysis of Wilson coefficient, which needs like a lot of more work. Then we can try to go to higher delta max in this TCSA approach, which requires more and more OP coefficient. And for this in field theory, there is like still a lot that we have to study. So removing these U effects, also. I've just shown you like the energy gap, but we can also study the ground state energy, trying to like look at the maybe a second bound state, and there is also a lot of work to do to improve the TCSA approach. And thanks a lot for your time. I'll just go back here.
We have time for questions.
I have a question about like one of the last slides we did. This one.
Yeah.
So indeed, the values of G tilde, C, G tilde, T prime that you extract look very stable. But can you explain? I mean, this is a nice way to present, of course, results. But if I just ran the full fit for the same energy levels involved, including G epsilon prime, what would have changed? Wouldn't I just get the same results? Maybe?
You would get like a very similar result. The only thing is that the reason why we tried like this more maybe refined analysis, because the fit was really unstable. I mean, if you include like like starting from 12 to 26 versus like 13 to 26, it was changing by 20% the result.
But that's what I don't understand, because
just because you're, I think it might be that it was the problem in which we are trying to fit, because we were trying to fit like lots of different powers. So some of them were really close to each other. So I cannot guarantee by the quality of the fit we were doing. Okay. I don't think it is like a conceptual thing. It's more like that you try to fit some powers which are really close to each other. So yeah. It's
Okay, thank you. No, this is nice.
There was like another question. Yeah.
I was wondering in the earlier part about the conformal generators. In our study with Slava and others, we basically found there are some level mixing effects, level repulsion effects. Do you also see them when constructing generators, that as a function of system sizes, but within ED ranges, like ED system sizes, that you see there's some kind of a permutation of selected levels? That what is a descendant of one and the other, their order actually changes with system size?
Yeah, okay. We haven't looked at like a lot of like the construction of generators for different n in particular, but we do see that when you you vary n, there were like a state where a spin 2 at one values of the truncation would maybe like a spin 0 at another value of n. This we noticed, but yeah, we haven't done this like refined analysis like as a function of n yet, but it's like a thing that we are planning to do.
Also, the cases where it makes the most difference that you look at it, something that's annihilated by k, is when there is a lot of mixing between different operators. So the state that is a primary picked out by annihilated by k is a linear combination of two nearby dilatation eigenstates.
Yeah.
So let's say you have a state that you know to be descendant. Is there a way to tell whether it's a descendant of, let's say, epsilon or a descendant of t mu nu? Like can you say what is the corresponding primary?
I mean, I think it's better like to work the other way around, in the sense that you start from what you define like a primary, and then because what we have access to is the full like you diagonalize the Hamiltonian, right? So we have energy eigenstate. So then you can try to start from the bottom, so the one with the lowest energy, and you define k, and then you just act with p with them. So you get access to the full state, and whatever you don't get, you get it like it's like a. Or another way to say is that whenever you just construct the null state of k, you already have all your primaries.
In the case of the 1 + 1 being Ising model, the deformation by the longitudinal field, I guess, is realized in experiments, and also it's integrable, so you know the answer.
Yeah.
Is there any other calculation of
this? Not as far as I know. I don't know if you guys are.
You mean in 2 + 1? Is there anything about deformation? We found maybe like 2 papers. Almost nothing has been done about it. Yes. We really, we tried to find, we could find almost nothing about deformation by sigma in around 3D.
Yeah.
But in 5 years, there's going to be hundreds of papers.
And therefore it's
So now the floodgates are open.
Yeah.
Can I ask another question? Can I ask another question? So would you go as far as to say that we should, so in the fuzzy sphere studies, that we should stop plotting energy eigenstates, but we should keep, from now on, we should always plot this?
I think it's like a sensible way to define primaries using our definition of generators, which is like...
Not just for primaries, you should say, okay, we should, since we know that the theory is conformal, you should first of all try to realize conformal algebra.
Yeah.
And then once you found the states, primaries, descendants, we should plot the expectation values of the Hamiltonian.
Yeah, that's part of what we would like to try, is like to try to compute like OP coefficient using primaries and descendant defined as we did, and see how these OP coefficients, for example, they look like.
And what happens? So you didn't present. Suppose that you take like the best state-of-the-art Ising data.
Yeah.
And you realize it in that framework. Would you get like even better agreement with Bootstrap, with everything?
I hope so, and I think so. Yeah. Okay. Until I don't see it, I cannot. I don't want to be falsified. But this is recorded.
Can travel to the future.
They will tell me later. So.
Okay. Thank you.
I don't see any other questions.
Okay. Let's have a brief.